Alejandro, go
on. Thank you. Hi, everybody. I want to start by thanking Anna for this wonderful organization. We all know how difficult it is to organize a meeting, and especially coming out of a situation like the pandemic. So thank you very much, Anna. This is running very smoothly and nicely, and we all appreciate it. And it's also very nice to be with you. Yes. It's also very nice to be in person after such a large lockup time. So I'm very happy to talk about this recent research that we've been carrying out for a long time, as a matter of fact. But these are the later results. And the general context are the heavy ion collision, the physics of heavy ion collisions, and in particular, the photon production in these kind of reactions. I'll show you that in particular, one of the observables that it's a bit complicated to understand has to do with the production of direct photons. And this is in the sense that the standard models that are used to describe this kind of probes, electromagnetic probes, seem to be not describing at the same time certain parts of the photon spectrum, the direct photon spectrum. In particular, the description of the flow coefficient V2 and the yield seem to not be simultaneously be able to be described. So this calls for some new ways of thinking about this observable, or to describe this observable. And what we've been thinking about during the last years is that perhaps the presence of large intensity magnetic fields could help to understand these properties. So this is work done in collaboration with Ana Julia here, Mariana Tejeda, Jorge Castaño, Luis Hernandez also here, and Renato Zamora. And details can be found in this reference. So let me start by quickly showing you an overview of the talk. After introducing the so-called photon puzzle in relativistic heavy ion collisions, I will talk to you about the idea that these photons may come from other stages in the evolution of the heavy ion collision, in particular from what it's called the pre-equilibrium stage. Then I'll tell you about how magnetic fields could, perhaps during this pre-equilibrium stage, help to enhance the photon production, but at the same time describe the V2. And for that, we need some theoretical tools, and what we've been working lately is on the description of the vertex of interaction that may produce these photons in the presence of a magnetic field, and this is the 2-gluon 1-photon vertex, which is a channel that is opened by the presence of a field. I'll talk to you about the general structure, in particular in the large field limit, and also some caveats of our approach, in the sense that in order to build this vertex, as I hope I can show you, it's a large and very complicated task, so we are doing it in steps. And so, although we don't have yet the yields and the V2, I think that we have the road to proceed along, and I hope that you guys can give us also some hints. And then I'll conclude. All right, so let's start by the facts. The facts are that the ALICE, together with the Phoenix measurements shown in this graph, give us a clear indication that the V2 of direct photons is, as a matter of fact, non-negligible. So both experiments, ALICE and Phoenix, so let me just tell you what this is showing. This is the V2 coefficient as a function of PT. And as you can see, both Phoenix here and ALICE, shown here in red ALICE and in green Phoenix, agree with the measurements of V2. And you see that this V2 is non-zero. It tends to zero when PT goes to larger values, larger than 4 GeVs. And this is done for different centralities and, of course, different energies. This is top rake energy and top LHC energy. And the puzzling thing is that the intensity of V2 is as large as that of hadrons. For instance, this is in red. These are this is the pion V2. This is for inclusive photons, but here on the right, you can see the same features for direct photons. So again, look, the intensity, the height of this V2 is pretty similar to hadrons, and in this case to pions than that of photons. So here we can more or less summarize the characteristics of this V2. So for PT larger than 4 GeVs, direct photons are consistent with 0. And this is expected if the dominant source of direct photons is the initial hard scattering. So in other words, if it was the opposite, it was the later stages, you will have time to build flow and therefore flow coefficients and therefore V2. But since V2 is 0 for large PT, then this is bound to be interpreted as that V2 was originated at the very early stages of the collision. And as I said, for PT less than 4 GeVs, there is a substantial direct photon V2, even comparable to that of hadrons. But then what about the spectrum? This is a yield. And this is a nice result from some time ago already that shows that in gold-gold collisions, you see that compared to PP collisions multiplied by the overlap function that takes into account the number of participants in the nucleus collision case, there is a substantial excess of direct photons here, which is clearly shown above this scaled function. So this is the yield, this is PT, and you see for low PT, you have a lot of extra photons. So this is interesting because it not only happens in gold-gold collisions, but it also happens in smaller systems, like, for instance, copper-copper. It's, again, the same. Here you have the PP data, and then if you multiply it by the overlap function, you don't get the description at low PT for the yields. And this happens, of course, in different centralities and also at different energies, as I will show you. So a bit of a summary of these results is that measurements at REC and the LHC show that the production of high PT direct photons in nucleus-nucleus collisions is consistent with the PP result scaled by the nuclear overlap function. And at low PT, this excess is attributed to a thermal component. So it's actually very tempting. This, in logarithmic scale, this is a straight line here. So the inverse slope may be attributed to a temperature. So in that sense, people think about these photons as providing a measurement of the temperature of the initial stages of the collision. Therefore, the inferred temperature in the early stages is as large as 220 or 300 MeVs from REC to LHC energies. So is this really a feature of the early history, the early thermal history of the collision? Well, I should mention that there is a tension between Phoenix and STAR, which is another one of the experiments that have been doing work on this front. So in fact, the yields in Phoenix are a little bit larger than those in STAR, although the V2 is very much into agreement. So if we go to Alice, for instance, in the case of Alice, this tension is not present with respect to STAR data. So in fact, the standard model, so to speak, of that describe these electromagnetic probes worked well, although you could say that perhaps at the lower edge of the statistical errors in these measurements. But nevertheless, it's important to keep in mind that there is this tension between Alice and STAR with Phoenix data. Here is a compilation, a beautiful compilation of Phoenix. This is a paper that just appeared this year. where what they do is to show results from gold-gold collisions at different energies. So for instance, this is 62.4 GeVs, different centralities. And if they scale the yields by the yield at a central pseudo-rapidity scaled at certain power here, then all of these data, different energies and different, same system but different energies, and no, even different systems, fall into this universal curve right here, which again shows a nexus with respect to the PP scaled data. So in any case, the message from this transparency is that this is there, and it seems to be, this excess seems to be there, and it is universal for different collision systems and different energies as well, of course, in the relativistic regime. So what? It seems that people would be reasonably happy with the fact that these are thermal photons, but nevertheless, in recent years, given this discrepancy between the description of V2 and the yields, people have been thinking about what happens if these photons come not from the early thermal stages, but from pre-equilibrium. So let me just briefly walk you through about the pre-equilibrium idea. So this is the state that is achieved in the very early stages of the collision, typically from 0 to 1 Fermi after the collision. So this idea was introduced by these colleagues in this work long ago, and it was introduced in the context of a bottom-up scenario for thermalization. So at the beginning, there is nothing like a thermal system, and then the system takes some time to relax to thermalization. But in the middle of this evolution, as I said, 0 to 1 Fermi, things get interesting. And in particular, the pre-equilibrium stage in nuclear collisions, although not very well known, what is known is that it contains a large number of gluons. So this is the main feature. Of course, it also contains quarks, but they are fewer because parametrically the gluon, the quark distribution is multiplied by a factor of the strong coupling, which in this case is smaller than 1. So you have more gluons than quarks in this stage. But nevertheless, what people say is, okay, so let's imagine that we have a quark and gluon distribution. These are not thermal distributions. They have been discussing a lot of options. One of them is that the distribution obeys a self-similar scaling, which is motivated by a turbulent approach to thermalization. So I'm not going to talk about these details, but in general, these occupation numbers are typically used to weigh 2-to-2 scattering processes that involve quarks and gluons to produce photons. Now, the problem with this is that, unfortunately, since there is no preferred direction in this context, there is no source of V2. In other words, in order to have a V2, you need something that points in a certain direction. So the upshot is that although the yield increases and gets closer to data, V2 worsens. And so this is shown in this, for instance, in this calculation by Monai. You see the idea of computing everything, photons from all of the possible sources, thermal, pre-equilibrium, and prompt, gives you this red line, which is worse than what the data show. Although the yields, which, for instance, were computed in this reference, improve a little bit. So if you include the pre-equilibrium photons here, you get closer to data. And if you do a little bit extra, you imagine that there is an extra enhancement of photons along the longitudinal direction, then you also get closer to this. Typically, these pre-equilibrium calculations show you this bump around what they use for the saturation scale. So let me not go into details. The references are there if you're interested. But so the idea is, okay, pre-equilibrium seems to be a situation in which you have a lot of gluons. And so what can be the consequences if there are lots of gluons, and at the same time we remember that at the very early stages of a collision, you can also have the presence of a very strong magnetic field. So if you, this is just a cartoon, of course, but if you think that at this pre-equilibrium stage, you don't have a plasma, you just have lots of gluons. The phase space occupation is large. And because of that, then you don't run into the troubles that have been recently discussed, in particular, for instance, by Igor or by several colleagues, that the medium, thermal medium, has an incomplete response to the magnetic field. So in the pre-equilibrium stage, that is not a problem. And so you have two bonuses. You have lots of gluons, and you have the largest magnetic field possible. So let's see what can happen if you do that. And this is work that we've done in the past, simulations with URQMD, that shows what is the time evolution of the field intensity. So this is just follow the classical trajectories of these charges in the nuclei that collide. And this is just to give you an idea of the scale. So pre-equilibrium will be from 0 to 1 Fermi. And during the first stages of the collision, you have the largest field intensity. So this is perhaps a good starting point. So the point is then, and this is the question, are there new channels for photon production opened up by the presence of an intense magnetic field at pre-equilibrium? And so we want to answer the question. And the answer goes through by noticing that if we have lots of gluons, then they can fuse and give you light, give you photon. And these kind of processes, although forbidden in vacuum because of Ferri's theorem, they are allowed in the presence of a magnetic field. Magnetic field, if you want, gives you an extra leg, vector leg in this triangle, and therefore it avoids Ferri's theorem. So the challenge is to compute this kind of processes. Notice that there is also a closely related process, which, if you turn around this triangle, gives you the gluon splitting. So it will also produce photons in the final state and will produce you a gluon. So we need to compute this object here. Yes, sure. But wait a minute with the microphone.
So if I understand correctly, this amplitude is proportional to the electric charge carried by wait. Yes, there's a quark loop inside, and this means that if you have 3 flavors, then maybe the sum is just 0. Is that correct?
No, it's not. No, you have 3 flavors, and then everything is coupled with the magnitude of the electric charge, not with the
magnitude. Why? But that
you go one way
photon,
and
yes,
then
quark
the other.
photon, yes, the
No,
vertex. There is only one
saying.
vertex, and so.
Yeah, I can give you details, but probably what you're saying is that you have to take this line this way, and then the other way, and then sum them up.
No. What I mean is, if you have the U quark loop, D quark loop, and S quark loop, then the U quark charge, D quark charge, and S quark charge, then I think that if you take the flavor sum, then this sum is just 0, I guess.
No, but I can give you details later.
Huh? Okay, but then the finiteness is just induced by the strange bulk mass effect. Okay.
All right. So the idea is then let's just stick to one flavor. So the idea is what is the general structure of this vertex, and in the presence of a magnetic field, the breaking of Lorentz invariance produces that space-time is separated into parallel and perpendicular components. So this is the metric here. And also, the 4 momenta of each of the particles that are participating is split into parallel and perpendicular directions. So these are the momenta associated to the external particles, photons, and these are the photons. The Q goes with the photons, and K and P with the gluons. And so each of them are separated into parallel and perpendicular directions. So we will be looking at a very particular vertex, and this vertex will be on shell. So first of all, there is momentum conservation. So the momentum of photon will be the sum of the momenta of the gluons. And because we are on shell, then we can find relations between these momenta. This is born out of momentum conservation. So the photon can be taken as the momentum of a photon can be taken as the independent variable, and the momenta of the gluons are proportional. given this ratio of their energies to the momentum of the photon. So what is the strategy then? What we want is to build this kind of diagram. So as you see, we have two gluons here and a photon here. And we want to do it at high intensities of the magnetic field. So one way of proceeding is to remember what is the tensor structure for, say, in this case, the two-point gluon function, and then add a third leg here, which will correspond to the photon. At high magnetic fields in the large field limit, then what you have is that the tensor structure is only singling out the parallel component. So this is what turns out from the calculation. So if we want to build a vertex in which you single out the large magnetic field scenario, then what you do is to add an extra leg here for the photon. And with this, you get one of the possible polarization states. Now, we know that this photon could be in 3 polarization stages, as discussed in this reference here. And these are assigned to these polarization vectors here. So the first thing we want to explore is what happens in the case in which you add the extra photon in the large field limit still. And it so happens that the only possible polarization that you can get is the transverse one, which is this vector here. Of course, if you relax that assumption, if you allow for B not to be the largest of the energy squared scales, and you let the photon energy to be comparable or even larger, this will not be the only structure that survives, but of course the computation becomes very large and very difficult. So for this work, what I'll show you is what happens if you just take this as the polarization vector that goes together with the parallel structure to build the triangle, and so the result is this vertex right here. What you have to do is to symmetrize all of the possible Lorentz indices, so the photon goes with one or the other, etc. And so this is the structure. So it's a tensor which is parallel in the parallel direction times a tensor in the perpendicular direction. All right, so you have to carry out the calculation in order to not have a vanishing result, and the reason why this transverse structure appears is to have one of the, in the large field approximation, it's to have 2 of these quarks in the lowest Landau level and 1 of them in the first Landau level. And so you do all of the possible combinations. And of course, you go ahead and I'll skip pretty much this transparency. You guys are all familiar with this. So this is the standard way of writing the propagator, the Schwinger phase, the Landau level representation, and the propagator in the Landau level representation, etc. So the computation then involves the sum of those diagrams that I just showed you, and this is here written. Of course, you have to write or to work in coordinate space and to integrate over all of the possible coordinates of the vertex. And if you work in the case in which the magnetic, this is a symmetric gauge, the magnetic field is pointing out in the Z direction, you compute what is the product of the phases, you carry out. And the results of this one loop level calculation can be written in this way. There is a prefactor here, and there is, of course, the tensor structure. What we did was to reduce this, in other words, just introduce notation, and we project this tensor structure that we get explicitly from the one loop calculation into the basis that we proposed, and this is the result. So let me just show you this. What I have here is, you see, the result is 2 terms. The sum of these amplitudes for n equal 1 to 3, these are 3 amplitudes, and so this guy here has these properties as a function of the energy of the photon divided by the mass of the fermion, and then as a difference of the energies here. So you see that for different intensities of the magnetic field, what you get is that this factor here grows with the magnetic field, but perhaps more interestingly is what is the angular dependence. So let me just concentrate on this guy here, which is, you see that for low energies, low momentum photon energies, you get, of course, a theta is the angle between the direction of the magnetic field and the direction of propagation of the photon. So you see that you have an enhancement for in-plane propagation that is pi halves. If this is the magnetic field and this is the plane of a reaction, photons tend to propagate in that direction. So I'm running out of time. I don't want to upset the chairman of the session. So let me just go to the conclusions. The main features of these results I just described. And so in conclusion, what we are doing is to pursue the writing of the on-shell 2-gluon 1-photon vertex that can be allowed in the presence of a magnetic field. And so if the energy of the photon is comparable or larger than the magnetic field intensity, then it seems that our approach is still incomplete. We need to put more tensor structures that allow for other polarization states. But nevertheless, the preliminary results show that at least some improvement can be achieved, and the characteristics of the spectrum that we are pursuing may be present here. So with this, I thank you.
Very simple and quick question. But so you focused on a very special process. But my question is, if you consider the coke production process, and then you can also have the photon Bremsstrahlung process. And I think that should be the same order. Why you focus on this process specifically?
We have to start from somewhere, Kenji.
But is there any physics argument why this should be the dominant process? Or?
Well, if you have photon Bremsstrahlung, what you have is quarks in the game. And so if you have quarks as free particles, what I just argued is that parametrically in the pre-equilibrium stage, quarks are suppressed with respect to gluons. So the first thing you have to look for is something that involves gluons
I understand. But anyway, in your process, you have the virtual quarks, right? And instead of that, you can also, from the the abundant gluons, you can also produce some quarks. And then, or actually, if you consider the CZC process, then there are lots of off-shell gluons also, right? Not only on-shell gluons. And so,
we have to start from somewhere.
Okay.
You know, this is a kind of complicated calculation. Yes, I agree. I mean, we have to explore all of these possibilities, of course.
Okay, so you took this
just
as a starting point.
Okay, and then we think about
I understand. Thank you.
It's a simple question about the approximations of the lowest Landau level. I'm trying to understand the range of the photon energies that you could calculate in this approximation. My understanding is it's not simply that the energies shouldn't be much larger than the magnetic field. That's one constraint. But I think they also shouldn't be much smaller than the magnetic field scale, because in that case you will have the processes dominated by essentially many Landau levels, high Landau levels as well. So can you say roughly what's the limit and whether this is enough to predict the excess?
It's a good question, and when you have the constraint of being at large magnetic fields, usually that is quantified in terms of the other scales in the problem. In particular, here it's the photon energy, but also the mass of the quarks. They are involved in the game. So you cannot go, in this case, if you're looking at the large field limit, then you cannot go for magnetic fields of order of the quark mass, for instance. So that's one constraint. The other constraint is that the photon energy couldn't be larger than the magnetic field energy associated with the energy. The problems we find here, the incompleteness of the calculation that I tried to portray, happens when the energy of the photon is larger than the magnetic field energy. So this is the part of the problem. So we are trying to fix it, and our impression is that if you introduce these other vector polarization vectors, then that should cure it. But we have to explore it.
Okay, thanks. If I may, that question that Kenji asked during the talk actually started bothering me.
Yeah.
Does it mean that if you put 3 diagrams with 3 flavors, that for the same masses of the quarks, The diagrams indeed cancel out? No?
So this is lowest Landau level approximation. If it is free propagated, then
So what changes if it's lowest Landau level approximation?
yeah, the magnetic field explicitly breaks that.
Oh, okay. Sorry,
There is no cancellation. In the presence of a magnetic field, there is no cancellation.
But that's based on what you said. That
It's because of the charge. Okay. Any other question? Yes.
Can you control the gates over what you're doing? Do you need more identities?
Yeah. Actually, that's the reason. That's a very good question. Thank you for the question. I didn't have time to go through. These, the way this is written is explicitly transverse. This vertex is explicitly transverse. If you contract with Q in any index, this gives you 0. So that's why we are building the vertex this way.
Okay. Let's thank again Alejandro.